Hello everyone, welcome back to Computational Nanophotonics videos. I'm Josh, and today I'm going to continue on with the Write Your Own 1D FDTD code with Python series. And before I get started, I just want to mention that I have uploaded the code for that last video, the last 1D FDTD video to GitHub. If you go to that video and go to the description, I do link to this GitHub repository, and you can find the 1D FDTD code that we wrote in that video. So it includes a material structures with a thin film of, I believe, silicon. It also includes boundary conditions, so mirror boundary conditions. It includes a unidirectional plane wave source. It includes reflection and transmission monitors and a movie monitor and all that stuff. And we'll be using this script in this video today. So let's get back to that. So today I want to talk about perfectly matched layers for FDTD PMLs. And the reason I want to talk about these is I want to move on to 2D and 3D FDTD. Well, not really necessarily eventually. Actually, I'm thinking maybe the next video or maybe 2 videos from now, I'll start with the 2D FDTD. And if we want to do that, we need to have absorbing boundary conditions. Now, as I mentioned last time, mirror boundary conditions are great for 1D, but for 2D and 3D simulations, we need something a little stronger. We need something that's going to absorb light at a bunch of different angles, regardless of polarization, and for all frequencies. So for that, we turn to the PML, or the perfectly matched layer. And this is a fictitious thin film of material that we place around the walls of our simulation domain, and it absorbs light that comes towards the boundary. So here's what that looks like. So here's our simulation. We have some sort of scattering object. We put light in here, and that scattering object scatters the light. So when that light hits our PML, because it's absorbing, as the light propagates through the PML, it's going to lose intensity. And the goal is that before it hits the wall, that intensity reaches such a low level that when it reflects off the boundary, the reflection will be negligible. Ideally, that reflection would be 0, but because we're working with finite differences and simulations and stuff, nothing's ever 0, so we go for a very small value. But how do we add loss to FDTD? Well, we add it. We do that by adding a current density to Maxwell's equations. So we add this Jx term to the Maxwell equation with the time derivative of the electric field. And the current density in the x direction is simply the electric conductivity multiplied by the x component of the electric field. But how does this actually cause loss? Maybe this is already obvious to you, but just in case it isn't, for a second, we're just going to ignore the space derivative of the magnetic field, and we're going to look at this part of the Maxwell equation. So this equation here is just a simple differential equation, and we can solve it. And here's the solution. So we get that the electric field in the presence of some conductivity sigma is going to decay over time exponentially, and the strength of that decay is proportional to sigma. Now, this is a very rough explanation of why sigma causes loss, but it should suffice for now. Essentially, if you have some sort of sigma value, you're going to get loss in your simulation. So this is what the Maxwell equation looks like with loss, with the conductivity. And we know from the last 1D FDTD video that our magnetic field is located at half time step, so at t plus delta t over 2. So because of that, this time derivative over here needs to be located at t plus delta t over 2, and this term over here also needs to be located at t plus delta t over 2. And from the last video, we know that The time derivative will be centered at t plus delta t over 2 if we pick whole time steps for the electric field. So the electric field here is located at t plus delta t and at t. This time derivative is thus centered at t plus delta t over 2. So perfect, that's what we want. But what about sigma Ex? So now we know that the electric field is located at whole time steps. So how do we get the electric field at this half time step, t plus delta t over 2? Well, the way we do that is we use a linear interpolation approximation. So we say that Ex at t plus delta t over 2 is simply the average between the electric field at t plus delta t and the electric field at t. So when we plug that into our differential equation, we get this. So this is our finite difference differential equation. And everything is centered at t plus delta t over 2. So we can then solve this differential equation for Ex at t plus delta t, so at the future time step, and we get this guy here. So what we're going to do now is we're going to divide by this term here, and we get an update equation. So Ex at t plus delta t is equal to some coefficient c times Ex at t plus some coefficient d multiplied by the y space derivative of the h field. And the c and d coefficients are just these terms here. Oops. Just these terms here. And notice that they actually have the same denominator, right? And that's just because of the denominator is just this term right here. Cool. And in index notation, so we replace the t with n, and replace like a t plus delta t becomes an n plus 1. All of our y positions become j's, and this is what the update equation looks like in index notation. And here we've included the space derivative of the magnetic fields. So for the PMLs to actually work, we also need magnetic field loss. We actually need a magnetic conductivity, and we're going to call that sigma star for now. And just remember that this is a fictitious conductivity. It's not real. We're just using it to absorb light. So if we do the finite difference approximation of this Maxwell equation, we get this big equation right here. So just remember that the electric field is centered at a whole time step t. So then this finite difference over here has to be centered at t, so we pick t plus delta t over 2, right, because the magnetic field is at half time steps, and t minus delta t over 2 over here. And we had the same problem over here with the location and time of the magnetic field, but we just use a interpolation to get the magnetic field at t. So again, we take t plus delta t over 2 and t minus delta t over 2, and we take the average of those two values to approximate Hz at t. And again, we can solve this for the future time step, and this is an index notation. Hz at n plus 1/2, j is just given by this c prime coefficient multiplied by the previous time step Hz plus the spatial derivative of the electric field Ex. And those coefficients are given below. And this is almost identical to the electric field update equation as well. All right, so this is what our FDTD algorithm looks like with this conductivity material. It's the same as in the last 1D FDTD video, except for now we have slightly modified update equations for the H and for the E fields. So our simulation domain is going to look something like this. So we have a light source, it's going to hit some sort of object, and then we have just this absorbing material all around of our simulation, so that when the light scatters, it's going to get absorbed by this material and not reflect back into the simulation domain. And we're going to, for the absorbing material, we use these conductivities. So how do we pick the electric and the magnetic conductivities? Well, we do that using electromagnetic theory. So to simplify things, I'm just going to look at the far right-hand boundary over here. So I'm going to zoom in on that. So we have two regions. We have this white dielectric region over here, and that's just the white region inside of the domain. And then we have our absorbing region over here. And to be general, I'm going to say that the absorbing region can have a permittivity of epsilon 2, which we don't know yet. And it's also going to have conductivities sigma and sigma star, which we also don't know yet. So in this dielectric region, we're going to have some light, and it's going to be coming towards our absorbing region. And because there's a general mismatch between the impedances, so our epsilons might not be the same. There's no sigma out here, but there's sigmas in here. There's going to be, in general, some sort of reflected field. But our goal is to have no reflection, or at least negligible reflection. It's FDTD, so there's never going to be no reflection, but we can make it as small as possible. So in order to do that, we need to look at the reflectance, and at normal incidence, so when light is coming in with no angle, the reflectance is given by this formula here, which is just the Fresnel reflectance coefficient. The eta terms are the impedances, so we have eta 1, which is the impedance of the white medium over to the left, and eta 2 is the impedance of the absorbing medium. And it looks a little more confusing when you look at the formula because it has these sigma terms. But if the sigmas were 0, eta 1 and eta 2 would look the same. So if we want the reflection to be 0 or as close to 0 as possible, then we need to set our impedances to be equal. We need our impedances to perfectly match. So that's where the term perfectly matched layer comes from. And if we look at the equations for the impedances, which I put in the bottom left-hand corner, we know that for them to equal, we need epsilon 1 to equal epsilon 2. We kind of probably already knew that intuitively, but it's good to derive it mathematically. And as for the magnetic conductivity, we now have this relationship here. So if we know the electric conductivity, then we can just set the magnetic conductivity using this equation. And these are our conditions for a PML. If we can set these, if we set up our FDTD with these conditions being true, we should get an absorbing layer that does not reflect light. So now the question is, how do we pick sigma? So we know how to pick epsilon 2, it's just epsilon 1. We know how to pick sigma star, so how do we pick sigma? Well, we want to approximate what the electric field in the PML looks like. So we're going to assume it's going to be a plane wave. So here we have e to the minus I k y, where k is the wave number, and y is just the y direction, right? In our 1D FDTD code, we're solving for the EX field in the y direction. So this first bit of the complex exponential is just a plane wave. And then the second bit here is the conductivity term. So it's the conductivity multiplied by y divided by the speed of light times the permittivity of free space. And if we want to look at the electric field intensity, we see that we get rid of the complex exponential, and now we just have this decaying exponential. So because of this sigma, because of the perfectly matched layer conductivity, we see that as the electric field travels in the y direction, it's going to decay exponentially. Now, we want the electric field, when it reaches the end of the PML, so when y hits L PML, we want that to be a very small number, and we're going to call it number delta. Now, ideally, delta should be 0, but because it's a minus exponential here, it's never actually going to hit 0. It exponentially goes towards 0, but even as y, if you can make y as big a value as you want, it will never hit 0. So we actually need to just pick a very small number, and that small number, we're going to call it delta. So we want EX squared at y equal to L PML equal to delta, and the delta is going to be a very small number, much less than 1. So then we just solve this equation. We solve this equation up here for sigma at y equal to L PML, and we get this equation down here. So we pick a small number delta, we plug it into this equation, and we get our sigma. Now, as I mentioned, it's tempted to be greedy. is tempted to ask for delta to be 0, right? If I plug 0 into this, ln of 0 just becomes minus infinity. So our sigma will be infinite. So we can't do that. We can't do infinities on a computer. Excuse me. So, also, if we pick delta to be a very small number, like 10 to the minus 100, let's say, then this ln function is going to be minus a very large number, right? So then sigma is going to be very, very large. We also don't want that, because if sigma is too large, we're going to get reflections. So the reason why we get reflections is purely due to the discretization. If FDTD were perfect, if we had a step size of 0, we wouldn't have to worry. We wouldn't have to worry about sigma being too large. But because we have a finite step size, if sigma gets too large, we will still see reflections even if the impedances are matched. So we need to pick delta strategically. It needs to be small enough so that the electric field decays within our PML, but not so small that we get reflections from the PML. Alright, so with that in mind, we're ready to implement a PML in our FDTD code. So we're going to take our 1D FDTD code from the last 1D FDTD video, and we're going to replace the MER boundary condition on the far right-hand side, so the far Y side, and we're going to replace it with just a PML with these two conductivities. We're also going to place a reflection monitor behind our source so that we can measure how much light gets reflected from our PML. And finally, at the far left-hand boundary, we're just going to have a MER boundary condition. So yeah, time to get to the code. Okay, so now we're going to take the FDTD code from my last 1D FDTD video, which you can find on the GitHub here. And I'm going to add a PML to the right-hand side of this 1D FDTD script. So the first thing I want to do is I want to add conductivity to my simulation domain. So where I'm going to do that is up here where I define all my fields. I'm going to add a sigma field. So sigma is equal to np.0, and it's going to be n space cells, and I'm going to add a magnetic conductivity too. So sigma, and I'm going to call it sigma sub h. And the next thing I'm going to do is I'm going to get rid of any sort of material structure. So I put in thin films last time, so let's just get rid of that for now. And just bring the refractive index up here. Okay. So the next thing we need to do is we need to make new electric field and magnetic field update coefficients. So here we have E coef and H coef. We're going to get rid of those. And we're going to bring in new coefficients. So I'm going to do that by bringing some stuff from off screen. So first things first, we're going to bring in the electric field update coefficients. And I'm going to start with the denominator. So here we have denominator is equal to epsilon times epsilon divided by delta t plus sigma over 2. And that just comes from the slides. Sorry. It's up here. Here we go. Right, so epsilon naught times epsilon divided by delta t minus sigma, plus sigma over 2, the denominator, and it's the same denominator for both of these coefficients here. Cool. And now I'm going to copy in those two coefficients. So instead of C and D, I'm just going to call those E coef 1 and E coef 2. And again, these are the exact same things that you'd find on the slides. And I put the step size in E coef 2 because you need the step size in the denominator for the derivative of the magnetic field. Sorry, you need the step size in the denominator for the derivative of the magnetic field. All right, so now I'm going to incorporate these E coef 1 and E coef 2 into the update equations. So E coef 2 is actually just going to take over the E coef position here. So E coef 2, there we go. And I'm just going to copy this guy here and place it, and I'm going to multiply this by the previous electric field, and this is E coef 1. So this is now our electric field update equation. It is quite long. But there you go. Now we need to do the exact same thing, but for the magnetic field. So I'm just going to copy the chunk of code from off screen because it's very similar to the electric field coefficient. It's almost identical, except for instead of epsilon 0 times epsilon, we just have mu naught. Okay, so now we got to put these h coefficients in the h update. So here, this becomes h coefficient 2. And we're going to put the same index as we have for the magnetic field. So put that in there. Then I'm going to copy and paste again. And I'm going to multiply hz previous by h coefficient 1. Okay, so we now have added in conductivities, but our conductivities are 0. But what I'm going to do is I'm going to run the simulation just to make sure that we didn't screw anything up. So I'm going to run the simulation. We're plotting the permittivity, but we got rid of any sort of interesting objects, so the permittivity is just going to be 1. So let's not plot that for now. Stop. Run. There we go. Simulation's running, and right, since we don't have a thin film anymore, I'm going to get rid of the thin film TR code right now. Gotta get rid of this line. Right, and now I'm going to comment out everything that's just not the reflection. So there we go. Now we're only plotting the reflection coefficient. Now let's run it. Alright, so here is our reflection spectrum, and it's 10 to the minus 22. So it's there's no reflection happening. And let's look at our simulation video. So we're going to see a plane wave being introduced on the far left-hand side here. And that plane wave is just going to propagate. So we've added conductivity to our simulation, but since the conductivity is 0, nothing's changed. And now we know we can watch this video. We see that FDTD is behaving as it should be, so we didn't make any mistakes in updating our update equations. Okay, so now let's add that PML. So first thing we're going to do is we're going to get rid of the boundary condition on the right-hand side of our simulation. So this line of code right here, get rid of it. So now we only have a boundary condition on the left-hand side. And now we're going to do our PML. So let's go up here. I'm going to uncomment this plotting, but I'm going to plot sigma this time. So we're not changing epsilon. Epsilon is just going to stay as 1 through this entire video. But sigma is what we're going to be plotting. Alright, so the first thing we need to do is define how big we want our PML to be. So in the slides we call that LPML, but I'm just going to call that PML size here. And it's going to be a number of cells. So that's just 10 PML cells. Next, we need to find out what our PML electric conductivity is. And remember, we have an equation for that. And let's go down. The equation, is this equation here. So I'm going to copy that from off screen into the code. So I'm going to call the conductivity PML cond E, so the electric conductivity. And my delta, I put it as 10 to the minus 3, so I'm really not being greedy. That is not that small. So it's minus ln delta times your speed of light times the permittivity divided by 2 times your refractive index times the PML size. So again, PML size is the number of cells, so LPML will be PML size times the step size. Finally, I need to occupy the sigma and sigma h arrays with those conductivity values. So the way we do that is we do this. So we have sigma from minus PML size. So this is going to the last 10 values of sigma and setting the last 10 values to being PML conductivity E. So we're going to have 10 PML cells. And now we need the magnetic permittivity. The magnetic conductivity. And again, it's similar line of code, sigma h, same index as before. PML conductivity E, and then multiplied by this term here. And that term there is the exact same as from the slides. Oops. Here. The magnetic conductivity is equal to the electric conductivity times mu naught divided by epsilon naught times the permittivity at the PML. And yeah, so that is what we have written down right here. Okay, so let's run this. So the first thing we see here is a plot of the electric conductivity. So you can see it's 0 for the entire simulation space except for the last 10 cells. So up here, you can see that we have 10 cells with non-zero conductivity. So we're going to let the simulation run. Okay, so this is our reflection spectrum. We can see that our reflectance is around 0.008, let's say. So there is some reflection. Less than 1% of the light that hits our boundary is reflected. So let's watch the video and see what that looks like. So we have our plane wave coming in from the left. Should really speed up the video, eh? It's quite slow. And now it's going to hit our perfectly matched layer. And here you go. So you can see that most of the light got absorbed by a perfectly matched layer, but we get still some reflection from it, right? So, and that's going to hit the Mur boundary, and the Mur boundary will take care of the rest. So we can see that our perfectly matched layer is not so perfect. It does reflect about 1% of the incident intensity. So one thing we can do to make it better is we can try to lower our delta value. So let's go down to, let's go 1e minus 4. Let's try that. Close that. Let the simulation run. All right, so, okay, so this plot's a little misleading. The actual value of this plot of the y-axis is let's say 1.3 e minus 2. So now we have more than 1% of the light being reflected. So if we watch the movie, we'll see a lot of light gets reflected from the boundary. So we asked for less reflection, but we got more. So that means that we're being too greedy. So that's what I mean. We can't set our delta to be too small. So 10 to the minus 3 was small enough. 10 to the minus 4 is too small, and it's going to cause us to have more reflections. So that's sad. Yeah, so there you go. You see the reflection happening. All right, so let's see. I'm going to make the PML now 10 times larger. Let's try this. So we're now going to run it. So now you can see the PML is bigger. All right. Okay, so now you can see our reflectance is now 0.0001. So what is that? 1, 2, 3, 4. So that's 10 to the minus 4. So that's now, actually, that's what we asked for. 10 to the minus 4 is exactly what we asked for. So that's great. So let's take a look at the video. So we see now that we've been, by increasing our PML size, we're now allowed to ask for more absorption. So let's see what that looks like. All right, I was gonna make the video shorter. So let's say now, sorry guys, every 30 slides. So here we go. The light's gonna hit the PML, and you can see now most of it's absorbed, and we get a little bit of reflection now. So let's see. Now that our PML is larger, let's see if we can ask for more absorption. So let's go with 10 to the minus. Let's go with 10 to the minus 6. Let's see if that happens. Maybe that's too greedy. We'll see. We'll see. Simulation ran. Okay, so yeah, that was too greedy because now our reflection went from 10 to the minus 4 to 2, or I guess 3 times 10 to the minus 4. So, okay, so now we're getting more reflection happening. So that's not what we want. Maybe 10 to the minus 5. Let's see. Sorry, running the simulation. Our plot's getting, okay, so here's what the spectrum, yeah, okay, so again, it's more. So delta of 10 to the minus 4 was about that's the least we can ask for, pretty much. All right, so if we try to go less than that, we're being too greedy. So as you can see, this PML is not very good, right? We gave it 100 cells, and it's still reflecting quite a bit of light back at us. And in a 2D or a 3D simulation, 100 cells is a lot. You don't want to be wasting 100 cells on PMLs. You want it to be about 10 cells. So this is the problem with our naive, simple, single conductivity PML. So when I go back to the slides, we're going to discuss ways to make that better. So we saw that our naive PML with the single electric conductivity and the magnetic conductivity wasn't the best. The reflection was still non-negligible. And one thing that we didn't discuss in the actual coding section, but I'll mention it here, is that our analysis from before assumed normal incident light. So in 1D, that's perfectly fine, but for 2D and 3D, especially with scattering problems where light can reflect at all the different angles, we're going to want more than normal incidence. So the first thing I'm going to do is I'm going to take care of this first point here. So the reflection is still non-negligible. One way we can take care of that is we can use a graded conductivity instead of a constant conductivity. So our graded conductivity looks like this. So sigma of y is equal to some sort of maximum sigma. And then we're going to start with, it's maximum sigma multiplied by y divided by the length of our PML to the power of some m. So at the beginning of our PML, where y is equal to 0, we're going to have 0 conductivity. And then as we go through the PML, that conductivity is going to increase. And that increase is going to depend on the power of m. And then at the end of our PML, so at y is equal to L PML, we then reach our sigma max. So our sigma throughout the PML is going to go from 0 up to some sort of maximum value. And that maximum value, we have an equation for it, just like last time. It's actually almost identical to the previous equation, only instead we now multiply by this m plus 1 term. So before, with a constant sigma, you can think of it as this, but with m is equal to 0. And if we plug m is equal to 0 into this guy here, we get the same equation as what we had before. Oh, except for one thing. I neglected to put the refractive index in here. But yeah, there we go. Now it's the same equation as before, if we set m equal to 0. All right, so that was a very quick slide break. Now we're going to a code break, and we're going to put in this graded conductivity terms. And again, we're going to see what that looks like with the reflection monitor and see how well this PML will absorb light. After that, we're going to add a PML on the left-hand side, only this time we're going to have to mirror those sigmas. So I'll show you how to do that in Python. And what we're going to do is we're just going to place a source in the middle, and we're going to make this a bi-directional source. So we're going to let the light propagate in both directions, and you'll see in the movie how these PMLs will absorb the light in both directions. All right, let's go. Okay, so now we're back to the code that we had before the slide break. So the first thing I'm going to do is I'm going to make a small modification to my PML conductivity. And I'm going to put in that m plus 1 term there. So m plus 1 times that. There we go. And I'm going to set my m. So if you guys don't remember, m is the power of this conductivity here. So it's y to the power of m. And so for m, typically you want to pick a value between 3 and 5. So I'm going to go with 3. M is equal to 3. Great. Now we want to make our conductivities graded. So the way we do that, again, I'm copying some code from our screen. I'm just going to multiply. So now this PML cond E is now my maximum conductivity. And now I'm going to multiply by numpy.arange. So what this is going to do is it's going to give me a list of values, or sorry, an array of values from 0 to PML size. So np.pml size, arange PML size divided by PML size. So, and then to the power of m. So this is very much the exact same equation as I have right here. To make it the exact same, what I'd have to do is I'd have to multiply the numerator by step size, and I'll have to multiply the denominator by step size as well. But since there's a step size in the numerator and a step size in the denominator, I can just get rid of that. So there we go. And similarly, for the magnetic field, I do need to do pretty much the same thing. So I'm just going to copy that from off screen. So we're going to have sigma h. So again, the same indexing here. It's going to be equal to the maximum conductivity, again, times mu naught divided by epsilon naught times the permittivity. Multiplied again by numpy.average of PML size plus 0.5. Again, so remember that the magnetic field is offset in space by the electric field. And we know that from the previous write your own FDTD videos. So that's why we have this plus 0.5 here. But again, other than that, it's pretty much the same as the electric conductivity with this extra term here. All right, so now we have a graded conductivity, and we're going to run the simulation. Okay, so let's zoom in. So this is a plot of the conductivity. Sorry, let me just zoom out again and zoom back in. So you can see here how the conductivity is now graded. So you can see at the very end of our simulation domain, the conductivity is at its maximum value, and it decreases to 0 into the simulation. So this should help us with those reflection errors. So we're going to run it. Let's look at the spectrum. Okay, so the spectrum gives us 10 to the minus, actually 8 times 10 to the minus, so 10 to the minus 5. All right, so that is actually much better than we got before. So before we were getting 10 to the minus 4. So let's look at the video with 10 to the minus 5 reflection. There we go. I made the movie faster too. And there's a tiny bit of reflected light. Tiny. You can still sort of see it in the movie. So now let's see, can we be a little more greedy now? So instead of 10 to the minus 4, let's ask for 10 to the minus 9. Not a little more greedy. I'm being a lot more greedy. So let's see. So again, here's our sigma. Letting it run. Here we go. So now you can see our reflection spectrum is now 10 to the minus 9. Almost exactly what I asked for. So if we let the simulation run again and we watch the video, the light is almost completely absorbed. We don't see any reflection anymore. So now we have a very functional PML. So with only 10 cells, we were able to absorb pretty much all the light. So the reflectance again was 10 to the minus 9. So that's very small. Let's see, can we ask for more? Let's go with 10 to the minus 10. Let's see, can we ask for... Let's be more greedy. Okay, no, we can't ask for more, guys. I'm sorry. So we went from 1.3 times 10 to the minus 9 reflectance to 1.4 times 10 to the minus 9 reflectance. So we've now reached that point where we're being too greedy. So 10 to the minus 9 seems to be our limit for this PML. Great. Okay, so close that. Now the next thing that we wanted to do is we wanted to place a PML on the other side of our domain. So we have a PML on the right-hand side, so now let's put one on the left-hand side. So the first thing we're going to do is we're going to get rid of that boundary condition on the left-hand side. And I'm going to get rid of that comment as well. Then we're going to go back to where we're defining our permittivities, sorry, our conductivities. And now we need to take these terms here and we need to flip them. So here's what I mean. So I'm going to say sigma, and I want this to be on the left-hand side now. So I'm going to go from 0 all the way up to PML size. And that's going to be equal to the maximum conductivity times this guy here. Now this guy here I want to flip this. So I'm going to do that. And then just because of index reasons, it's hard to explain, but just go with me here. We're going to add a +1 here. So we just numpy.flipped the term that causes the conductivity to increase, because now on the left-hand side of the domain, we want the conductivity to decrease. So we want it to be maximum at 0 and then minimum at PML size. So that's why we numpy.flipped. And we need to do the exact same thing, but for the magnetic field. And I'm going to copy that from off screen. So this sigma h here from 0 to PML size, it's almost exactly the same as this sigma h up here, only I'm putting a numpy.flip inside. I'm wrapping this argument here with a numpy.flip, so that the sigma h goes from maximum to minimum on the left-hand side. And now that that's done, one more thing I'm going to do is I'm going to make the source not unidirectional. So I want the source now to propagate in both directions. And I'm going to put the source now, JSource, I'm going to put it in the middle of our simulation domain. So n space cells divided by 2. So now what we're going to see is we're going to see the source in the middle of our simulation domain. It's going to propagate light in both directions, and we're going to see that both of the PMLs will absorb the light that hits them. So here we can see now on the left-hand side, we have non-zero conductivity. And because of, so it's hard to describe what the sentence means, but the FDTD grid is asymmetric sort of. So because of that, you'll sometimes get that the conductivities are different on both sides. The maximum conductivities are different on both sides. I wouldn't be too alarmed. Actually, there's a way to fix this. Let me fix this for us real fast. So here, I'm going to divide by PML size +1. Just because I have that +1 in the numerator, let's just divide by PML +1. And then I also need to do this for the magnetic conductivity. So let's do that. Alright, so now, again, because of the asymmetry, the conductivities, the maximum conductivities are slightly different on both sides, but they're now roughly the same. But yeah, so if we zoomed in on the left-hand side, we can now see that the conductivity is graded on the left-hand side. Alright, and it's flipped, right? So it goes from big to small, and then on the other side of our simulation domain, let me just zoom out. On the other side of our simulation domain, it goes from small to big. So that's why we did the numpy flip. Alright, finally, enough talking, let's let it run. Ignore the spectrum for now, and here's our simulation video. And we can see that light went in both directions, and it got the light got absorbed by the PMLs on both sides of our simulation space. So the PMLs work. So we already saw that the reflectance on the right-hand side PML is 10 to the -9. But what about the reflectance on the left-hand side PML? It should be roughly the same, but we should still quantify it to make sure that everything's working fine. So we're going to do something a little special here. So here I put the magnetic field source back in. So now the electromagnetic field will travel unidirectionally again. But I want it to travel unidirectionally in the opposite direction. So instead of traveling to the right, I want it now to travel to the left and hit that left-hand PML so I can measure the reflection from that left-hand PML. So I'm going to modify the magnetic field source. And the way I do that is I'm just going to add in, sorry guys, I'm going to copy it from off screen here. So I'm going to comment out this guy here. So here is the new magnetic field source, and this is for left-hand traveling light. So it's very similar for the right-hand traveling light magnetic field source, only instead of the here, let me uncomment. So instead of the minus sign up here, we have now a plus sign down here. And instead of a minus sign for the t offset, we have now a plus sign for the t offset. But we introduced the source at the same spot, but now with a plus sign and a plus t offset, and that's going to cause light now to travel in the left-hand direction. And if I want to measure the reflected light from that left-hand PML, I also need to measure. I need to move where I place my reflection monitor. So I'm just going to place my reflection monitor JR at n space cells minus the PML size. So I don't want the reflection monitor to be in the PML. And I'm going to put it 10 cells away from the PML. Oh, you know what? That's silly. Let's just do this. Instead of that, I'm going to do JSource plus 5 instead of, there we go. That's better. So now, again, our reflection monitor will be behind the source. Okay, so let's try this. So we're going to run this. Again, our source is going to be around cell 2000, and it's going to propagate light in the left-hand direction. And this is the reflection coefficient of our left-hand PML. So now you can see that it is 7 times 10 to the minus 10. So that is, again, roughly 1 to the minus 9, which is what I asked for. You'll notice that the left-hand PML is a little more absorbing than the right-hand PML. And again, that's just because the FDTD domain is asymmetric. But again, they're both very small numbers, so it doesn't really matter. So let's let it run. Let's let the movie run. And you'll see, now we're introducing light to the left-hand side. And there we go. So yeah, in this video, you got a bit of a 2-for-1 here. We introduced the PMLs, and we also added in a source that propagates in the left-hand direction. And you'll only know that if you reach this point of the video, so good for you. All right, so we've completed the goal of this coding session. So we've added in a graded conductivity for our PMLs, and we show that that greatly reduces the reflection, almost miraculously so. And then we added in a left-hand traveling wave, and we added in the left-hand side PML. So now we've taken care of our first issue. By using a graded conductivity, we are able to show that we can reduce our reflections significantly. So now the reflections from our PMLs are negligible. However, we still have a problem. Our analysis in deriving the PML assumed that light is coming in at normal incidence, which again is fine for 1D because that's all you have is normal incidence. But for 2D and 3D simulations, we can imagine that light can come in at different angles. So remember before, right, when we talked about the reflectance earlier, and I said that eta 1 must be equal to eta 2. Well, this equation here assumed that light is coming in at normal incidence with theta, with the angle equal to 0. But again, in 2D and 3D simulations, we can expect that the light's going to scatter off some object, and it's going to come at our PML at an angle. And we can expect that there's going to be some reflected light, and that reflection is going to depend on an angle. So it's going to, depend on the angle from Fresnel reflection theory that you should have learned in optics or electromagnetics. So the way that we take care of this is we're going to use something called the stretched coordinate formulation. So this is, so let me just go full screen for a second. Here we go. So the stretched coordinate formulation is where PMLs get a little more complicated. So a lot of people don't like to talk about PMLs because they can be tricky, and the stretched coordinate formulation is kind of one of the reasons why that is. So let's just go through it slowly, and hopefully it's understandable. So we're going to start with our electric field in the PML. So again, we have EX, it depends on Y, because we're doing a 1D simulation. And we know that the electric field is going to be a plane wave, right? So e to the minus IKY minus this loss term that's caused by our conductivity. This assumes, though, however, that our conductivity is constant. If our conductivity depends on Y, our equation becomes something like this. So instead of there just being a sigma times Y, we now have this integral of sigma with respect to Y. So what we're going to do is we're going to create a coordinate transformation that lets us describe this decaying electric field as simply a plane wave. So we're going to embed this loss term over here into this y hat coefficient. So our y hat is simply just y minus this guy over here, our I over omega times epsilon naught times the integral of our permittivity, or sorry, of our conductivity. And just know, so if you plug this y hat into this plane wave here, you'll get this equation up here again. So that's where this transformation comes from. So basically what we're saying here is we're going to, in our PML region, we're literally going to make space complex. Maybe that's a little confusing, but just know that by doing this, we are basically forcing our fields to be absorbed in that region of space. So wherever we make this transformation, we're forcing absorption to happen. So again, we're making this transformation of our coordinate, and that's the stretch coordinate formulation transformation. And that means that the derivative with respect to this y hat is now equal to 1 over this guy down here times the derivative with respect to y. So if we replace d by dy with d by dy hat in our PML region, we are guaranteed to get loss in the PML. Right, and instead of carrying around this big 1 over blah term here, we're just going to call this blah term sy at y. So right, we defined sy at y to be 1 minus I over omega epsilon naught times sigma at y. But it is actually common practice to add a little more flexibility. So we're going to replace 1 with a coefficient kappa y, which is a function of y. And in our denominator here, instead of just being omega epsilon naught, we're going to add this ay term here. So again, so kappa y physically should be a 1, and ay physically should be a 0. But if we actually set those to be alternative values, we get better PMLs, as it turns out. And that was just something discovered by people back in like the 80s and 90s and stuff. So. Okay, so in the PML region, this is what our Maxwell's equations look like. Now, I wrote them out in frequency domain, so I replaced the time derivatives with I omega. Hopefully that's okay. Hopefully you understand why that is. And over here, you can see I replaced the space derivatives with d by dy hat. Oh, right, and the reason I'm using frequency domain is because our y hat depends on frequency. So if I go up here, right. Actually, let's just go up. So here you go. Our y hat is given by y minus I over omega epsilon naught. So this omega here, right, means that our y hat actually depends on frequency. So to write Maxwell's equations correctly, we need to write them in the frequency domain. So to put this back into real space so we can solve it in FDTD, we then need to include those 1 over sy terms here. And again, it's in the frequency domain because sy depends on omega. All right, so if we want to solve this in FDTD, we need to do a Fourier transform. We need to go from the frequency domain to the time domain. So wherever you see an I omega, just change that to d by dt, and now you have a Fourier transform. And again, this is Maxwell's equations only in the PML. All right, so first, there's two things to look at here. So first things first, we have these sy at t functions here, and that's just the Fourier transform of 1 over sy at omega. All right, well, that should make sense. However, what we also have here are these star operators. So these are convolution operators. So this tells me that we need to do a convolution integral of sy at t with the derivative of the magnetic field. So this leads us to the CPML, also known as the convolutional PML, because there's this convolution here. And the CPML is just an efficient algorithm to solve these equations in the PML region. So I'm not going to go deep into the math about all this stuff. I'm just going to skip a few steps. So basically what we're going to say is using sy at sy at t and y, is equal to the Fourier transform of 1 over this guy here. So again, that's just the Fourier transform of 1 over sy at omega, where sy at omega is given by this formula here. All right. So if you take this Fourier transform and you plug it into Maxwell's equations and you actually do some convolutions and you do a bunch of math, and again, you can find all that math in chapter 7.9 of this book here. I've recommended this book before. If you're doing FDTD, you should have this book. Anyway, so see chapter 7.9 if you want to understand the math that goes into this. But we go from these Maxwell's equations here to these Maxwell's equations here. So this is a lot easier to look at. So there's no convolutions here anymore. So we have our regular Maxwell's equations, except for where we see our derivatives. We now have this 1 over kappa y, which is fine. This is no longer a convolution. It's literally just multiplication. And then we have this plus psi, this plus psi at t function here. And we have a psi for the electric field Ex, and we have a psi for the magnetic field Hz. And again, all of this is only in the PML. Outside of the PML, we can solve the regular Maxwell's equations. But now we need ways to calculate our psi's. Luckily, we have update equations for the psi's. Okay, so again, I'm not deriving this stuff. I'm just giving it to you. So if you know psi Ex, comma y at t, y, so at some time step t, then you can calculate psi at the next time step, t plus delta t. And it's just this update equation here. So you need the psi at the previous time step, and you need to calculate the derivative of your Hz field, which again we do using finite differences. And these by and cy coefficients, I'll show you what those are in a second. Similarly, the psi Hz also has a very similar update equation. So again, if you know psi Hz at t, you can calculate t plus delta t. And that depends on the electric field, the derivative of the electric field with respect to y again. And we have the same coefficients, this by and cy coefficient. And here's what those by and cy coefficients are. They're a little ugly, but they are just functions of the guys we already had. So we have our sigma y, we have our kappa y's, we have our a y's. We know delta t, we know epsilon naught. And once you calculate by, then you can calculate c at y. And c at y depends on b at y, right? You can see it here, b at y minus 1. Again, we'll do the code for this, so don't worry, you don't have to memorize these equations. Finally, we should mention our sigma, kappa, and a functions. So again, our sigma y is that graded conductivity that we talked about before. Our kappa y is also graded. So you choose your kappa max, and then your kappa y is just 1 plus kappa max minus 1 times this grading. And what this all does, it makes it so that in the non-PML region, so where y is less than 0, so to the left of the PML region, our kappa y is just 1. And finally, this is the ay function here. So it is also graded, but it's graded in the opposite direction. So sigma and kappa, these functions grow as we go through the PML. A will shrink as we go through the PML. So it's flipped, LPML minus y. And here are some values that you can use for all these numbers. So m, I typically use 3. MA, so that's the exponent up here. I usually use 1 for that. Kappa max, I usually use 5. And A max, I usually use around 0.05 or something. So finally, we have our finite difference update equations for our Maxwell's equations in the PMLs. And so they're very similar to what we had before. So Ex at n plus 1 depends on Ex at n plus, so here inside the brackets we have first our magnetic field derivative with respect to y, and we have this kappa y term. So again, this kappa y term is going to be 1 everywhere in the FDTD domain except for in the PMLs. It's going to be bigger than 1 in the PMLs. So everywhere that's not the PMLs, we expect the regular derivative of h with respect to y. And then we have plus this psi term here at n plus 1. And this psi term at n plus 1 is just given by the psi term at n plus, again, the derivative of the magnetic field. And again, we have a similar updated equation for the magnetic field and psi of the magnetic field. So here is our algorithm for the CPML. So first, we need to set up our sigma, our A, and our kappa for those Y PMLs. And those will help us derive those B and C terms. Then we do our time stepping loop, and we'll update, first we update our psi for the magnetic field in the PML region. Update our psi in the PML region. And then we update our magnetic field, including that psi. And this psi will be 0 everywhere that's not the PML. So we can just include it in the regular update. And since it's 0 in the regular FDTD domain, it won't affect this update equation. And we do the same thing for the electric field. We update psi first, and then we include that in our electric field update equation. And this is the CPML. I believe this is kind of like the industry standard in PMLs for FDTD code. So if you're using MEEP, if you're using numerical or tidy 3D, this is the PML that they're probably using under the hood. All right, let's implement this PML in our code. So again, we're going to start from the FDTD code from our previous code break where we have our graded conductivities here. And I'm just going to actually just delete all of this code here because we don't really need it anymore. All right, so we have our maximum conductivity, which is going to stay the same as from last time. Remember, we have that A function and that kappa function, so we need the maximum value of A and kappa. So I'm just going to copy this from off screen. So we have our A max and our kappa max. And as I said before, A max, I'm just setting it to 0.05. You could probably set to 0.1 or something. And I'm setting my kappa max to be 5. Again, I highly recommend you play around with these parameters and maybe see if you can find a PML that's better than what I have. Almost guarantee you can. I don't think I played with these parameters that much. Okay, so now we want to set up our sigma, our conductivity function for the PML. So that's going to be like we had before. So I'm just calling this sigma PML. It's going to be equal to our maximum conductivity, same thing as before. And then we have, again, this numpy A range term. So this is going to be a list from 0 to PML size, divide by PML size to the power of m, where m is just 3. So this is what we had before for our sigma. Our A, actually let's do our kappa function next. So our kappa function, if you remember from the slides, here it is. It's just 1 plus kappa max minus 1 times the grading. So let's open up, there we go, and we're going to copy this in. So I'm calling this kappa underscore f, which I'm just going to say this means kappa far. So this is for the right-hand side of the simulation domain, so for the positive y side of the simulation, kappa underscore f. And finally, we need our A function, which I'm just going to call A PML. And this is going to be A max times, and again, so now we have the grading again, but we have the negative grading. So we're doing PML size minus numpy.arrange PML size. And again, that's just from the slides. You can see it's PML size minus y. So that's where that comes from. And I'm putting this to the power of 1. So there's an MA in the slides. I'm just setting MA to be 1. Okay. And now we're going to do the exact same thing, but for our magnetic fields. So we're going to do the same functions, but the magnetic field version. So sigma H PML. So that's exactly the same as sigma PML, but it's going to be offset by a half, right? Because again, the magnetic field is at half space steps. And we're going to do the same thing for our kappa H. So again, it's the same as kappa up here, but it's with the half step, and same thing with our A. It's just with a half step. All right. With those out of the way, I'm now going to calculate those B and C coefficients for the PML updates. So let me just bring those back up again. So remember, for these psi updates, we need this B and we need this C coefficient. And those are given by these equations here. I'm just going to copy those and paste those from off screen. So let's just do that. So here is the B for the electric field. So I'm saying B underscore E, so that's B for the electric field, underscore Y, so that's for the Y PML, and underscore F. F means far, so that just means the PML on the far right hand side of our simulation domain. And that's equal to numpy.exponential of our sigma divided by kappa plus A PML times delta T divided by epsilon naught. And that is just this function right here. And we can do the same thing with our C. So we're going to copy that from off screen here. So this is again C for the electric field for the YPML on the right hand side for the far side. And that's just this equation here. And this equation you can confirm for yourself is just this guy down here. And we're going to do the same thing for the magnetic fields. And it's the exact same equations, but where everything is underscore H. So sigma underscore H PML, kappa underscore H underscore F, and A PML underscore H. All right, so there we go. We have now our update equation or update parameters for the PML on the far side of our simulation domain. Now let's do the same thing, but now for the PMLs on the near side, on the left-hand side. So we need to recalculate sigmas, kappas, and the A's for the electric field and for the magnetic field, and we need to flip them again because we want the profiles to be in the opposite direction. So I'm going to copy that from off screen, and here we go. So here, okay, so actually I'm going to add some notation real quick here. So some comments. PML, PML for the far Y side, okay? And then down here, we'll have PML for the near Y side. So over here, we had sigma PML, and we had numpy.a range from, so that goes from 0 to PML size. So over here, sigma PML, I'm going to have PML size minus that numpy.a range. So again, we're flipping that we're flipping that conductivity profile. And we're doing the exact same thing for APML, so we flip that, and we're doing the exact same thing for kappa. So APML will now increase instead of decrease, and kappa will now decrease instead of increase. And same thing for the magnetic fields. And we're going to have now our B and C coefficients for those near PMLs. So here we go. Again, the same equations as I used up here for the far, I'm using down here for the near. And I'm not going to bother with the underscore n for near because who cares? Finally, I'm going to get rid of this plt.plot of sigma because we don't really need that anymore. Okay, so next thing we need to do is we need to declare memory for those psi vectors, those psi arrays that we were talking about before. So we're going to define those up with our electric field and magnetic field. So I'm going to say p underscore ex sub y, and that's just going to be numpy.zeros with the number of space cells. And we need that same psi for the hz field in the YPML. Okay. And again, most of these, this PEX sub y and PHZ sub y, it's mostly going to be zeros, but only in the PML region will these guys be non-zero. All right, and then finally, we need to define those inverse kappa terms. So if we go back to our Maxwell's equations in the PMLs, here we go. So yeah, we define these psi terms here. Great. We now need to define these kappa terms, these kappa y's. So I'm going to define an inverse kappa dy. That's what I'm going to call this guy, and it's going to be ones across most of the simulation domain, and again, it's going to be not one in the PML regions. And because the H field is also offset from the E field, I'm going to create a kappa H vector as well, which again is also just going to be ones for now. And we're going to go down here, and we need to set those inverse kappa guys to be not one in the PML regions. So let me copy that from off screen. So first things first, we're going to take inverse kappa dy, and we're actually going to, so since it's ones right now, I'm going to divide by equal to the step size. So I want this inverse kappa dy to include that step size in the denominator. So it's going to include kappa y, and it's also going to include the delta y down here. All right. Similarly, I'm going to do the same thing with the H kappa. Okay, now let's include those PML terms. So inverse kappa dy for the electric field from minus PML size up to the end of the domain. So this is for the far right-hand side PML region. That's all going to be equal to 1 over kappa far, again, far right-hand side, times step size. And for the near PMLs, for the near PMLs, it's the same thing. Only instead of kappa f, we now have kappa, which is the same thing as kappa f, but just flipped. Hit the microphone there. Finally, let's do the magnetic field kappas. I'm just going to copy those from off screen. And here are those inverse kappa h's for the magnetic field. And again, we have kappa hf for the far PML, and just kappa h for the near PML. We shouldn't have to change anything else in the precursor code. Now we need to change our update equations. So first thing we need to do is we need to update our PML, our psi fields. So we're going to update the psi field in the far PML region first. So I'm going to copy that code from off screen. Okay, so this might look a little complicated, but just look. It's just our psi hz underscore y at the new time step is equal to b times our psi at the previous time step plus c times the derivative of the electric field with respect to y. And that's the exact same update equation I had in the slides. So yeah, psi at h for the current time step is equal to b times the previous time step psi plus c times that space derivative of the electric field with respect to y. Oops, sorry. There we go. So that's this line of code right here. And now we need to update the PML in the near y region. So it's the same update equation. So here we have psi hz sub y. Again, it's just equal to b, but for the near. Instead of b sub f for the far, it's b for the left side of our simulation, for the near side of our simulation. So it's b times psi at the previous step plus c times that electric field derivative again. So we have the first line is for the far PML, the second line is for the near PML, or for the plus y PML and the minus y PML, however you choose to think about it. And now we need to change the magnetic field update to include those psi's. So remember the magnetic field, so this magnetic field Maxwell equation, we need to add in, first of all, we need to add in this inverse kappa term here, and we also need to add in the psi hz y. So let's start with the kappa term. So first thing I'm going to do is I'm going to make this a 2-line update equation. And I'm going to wrap that in brackets. Okay. Now we need to go find H coefficient 2, because H coefficient 2 has step size here. So I'm going to get rid of that because we've included that step size in our kappa coefficient vector. So I'm also going to do this for the H coefficient 2. So just get rid of the step size here. Perfect. And I now want to multiply this electric field, this finite difference of the electric field by that kappa H term. So I'm just going to copy that from off the screen. Okay, so that's going to look like this. So here I just took that inverse kappa H sub dy, and I used the same indexing as I do for the magnetic field here, and I multiplied that by the electric field finite difference. Okay, and the last thing we need to do is now add in that psi term. So I need to add in extra brackets. So there. Okay, so plus, and then we're going to add plus psi hz sub y with, again, the same index that we're using for the hz. Boom. And there we go. So this is now we have our psi hz updates for the near PML and the far PML. We have our hz update, which includes the PML term here and that kappa term. Okay, now let's do the electric field update. And so I'm just going to again copy and paste some stuff from off screen here. So here is our psi for the electric field. So psi ex sub y. So this is for the far PML over here. So that's why we have the underscore f's. But again, it's just b times psi at the previous time step plus c times the derivative of the magnetic field with respect to y, and that's for both PMLs. Okay, and then again, I'm going to make the electric field a multi-line update now. And again, we need to multiply, so I'm just add another pair of brackets here. Bracket there, bracket there. We need to multiply the hz finite difference by the inverse kappa. So copy that from off screen here. Times inverse kappa dy. And move over here. Bring this over here. Plus, and we're going to add that psi ex sub y. Psi ex sub y with, again, the same index of our electric field update. So 1, 2, and space L's minus 1. So that right there is your CPML update. I guess we should see if it works. So let's run it. I think we're going to run it. I'm going to get rid of the magnetic field source. So we're going to run it with the source in the middle again. And we're going to let the light propagate in both directions and see if both PMLs work using the movie. Oh, apparently not, guys. So we have some sort of instability here. So our electric fields went to infinity, or not a number. Yeah, okay, so let's stop the simulation from running. And it's time to debug. Right, okay, so it took me a second there, so I cut, but the mistake is I just need to put an extra bracket here. So put a bracket beside the inverse kappa dy, and then I'm just going to put a bracket at the end here. I was just missing a bracket, guys. So with that bracket now included, we can run our simulation. And now we can see that it's stable. Our electric fields don't go to nan. They remain numbers the entire simulation. We're going to ignore the spectrum for now, and we're just going to watch the movie. So here we have our wave being introduced in the middle. It's propagating in both directions. And you can see that none of the light got reflected back into our simulation. So the light hit the boundary, and it was completely absorbed. So as you can now see, our PMLs work. So now let's quantify how well they work. So the way we do that is we're going to bring back the unidirectional propagation, and we're just going to measure the reflection from the boundaries. So let's do that. So we're going to bring back, I don't know which direction I'm making the light travel. Let's just watch the movie and see. Yeah. So we're making the light travel in the forward direction now. Okay. So our reflection coefficient, we want to measure our reflection now behind the source, so J source minus 5. So let's run the simulation again. And now we'll look at the spectrum. All right, so here you can see that our spectrum is centered at 1.27, so 1.3 e minus 9. So that's 10 to the minus 9 is our reflection coefficient for the PML on the right-hand side of our simulation domain. So that's pretty much exactly what we had before with that naive but graded conductivity PML that we had before. But this PML now, the CPML that we've just implemented, we can put this into a 3D FDTD code and it'll absorb just as well. So yeah, if we watch the movie, we'll just see the pulse coming in and it gets absorbed by the PML. Perfect. And now we're going to go into the left. We're going to send in our light to the left-hand direction, so we need to move our reflection monitor to J source plus 5. And we're going to change the magnetic field source so that it's going to inject light to the left. So let's run the simulation and see how well that left PML works. All right, so just like before, this left PML now has a reflection coefficient of 1.3 times 10 to the minus 9. And yeah, you can watch the movie now, and we see the light propagates and gets absorbed. Perfect. So this time, I was able to get the PMLs on the right and the left-hand side to have the exact same reflection coefficient, so 10 to the minus 9. And again, these PMLs should work regardless of the permittivity. So what I'm going to do is I'm going to set the permittivity, instead of 1, I'm going to make it just a constant permittivity of, let's say, 2. And we're going to run the simulation again and make sure that our PMLs absorb the light. All right, so here we go. We can see our reflection coefficient is now 2 times 10 to the minus 9. So our PML got a little worse, but it's still pretty good. 10 to the minus 9 is really good. So we can watch our simulation, and we're going to see that the wavelength looks a little smaller this time because the refractive index is not 1. But yeah, the PML still works. So one thing that we should understand is why, if we increase the permittivity, why our PML works a little worse. And it's purely because, sorry, let me just find the right slide. Right here. Remember when I talked about loss near the beginning of the video here? We said that EX is proportional to this decaying exponential here. Well, if I increase the permittivity, we can see that that's going to negatively affect the loss. So that's going to make the loss less. So it'll make our PML less effective. So that's why when I increase the permittivity, we see a less effective PML. But that's okay. It's less effective, but not that much less effective. And let's see what happens if I put the permittivity at 4. Yeah, so again, by increasing, so yeah, it seems that if we double the permittivity, we double the reflection. But we're still 10 to the minus 9, so we're still really, really good. Perfect. Yeah. We don't really need to see the movie anymore. You know what it'll look like. So that's it. Yeah, this is, I've introduced in this video PMLs for FDTD. So first I introduced a simple constant conductivity PML. Then I showed how we could improve the reflection coefficient by making the conductivity graded. And then I showed us how to I showed you guys how to do the convolutional PML, the CPML, which we implemented here in the code. And we can use this PML in 2D and 3D FDTD simulations. Right, so before ending the video, I just want to talk about 2D and 3D FDTD simulations with these PMLs. So let me just find where I was before. Alright, so this is where the code break was. So, right, the PML in 1D, we just need to solve Maxwell's equations like this, where we include this 1 over kappa term with our space derivative, and we include this psi. In 3D, however, we're going to now have PMLs in the x, y, and z directions. So, we'll have to apply that stretched coordinate transformation to our x, y, and z directions. So here you can see with the electric field update, we can see the stretched coordinate transformation applied in the y direction, as we've already done. But we also have it now applied in the z direction, because the electric field, the derivative, this Maxwell equation for the EX field includes a derivative with respect to y and a derivative with respect to z. So we need to account for the stretch coordinates in the y and z directions. Right, so this is what that looks like here. So you can see here's a 2D simulation domain, and with the y being the propagation direction and the z being the upward direction here. And you can see that we're going to have this psi EXY in the left PML and the right PML here. And we're going to have this psi EXZ in the up PML and in the down PML. So we'll have psi EXY in the y PMLs and psi EXZ in the z PMLs. But what's interesting is that we don't need to account for the x PML for EX. So yeah, out of the screen and into the screen, there would be an x PML for a 3D simulation, right? But EX will not feel that PML. So this is what the EY update equation would look like. So again, this is just Maxwell's equations, but for the EY component. And again, you can see here that we have this stretch coordinate representation for the z direction and for the x direction, but we do not need it for the y direction. So for EY, we only, the EY component only feels the PMLs in the x and z directions. And finally, for the EZ, it will only feel the PMLs in the x and y directions. But the equations are pretty much the same thing. So we can, if we could apply the PML in one direction, as we've already done today, in the y direction, you can apply PMLs in all the directions. Okay, right, so this is just summarizing what I just said. So the E and H field components only feel the PMLs in the orthogonal direction. So for EX and HX, you only have to account for the Y and Z PMLs. So again, we're solving for we're solving for EX in our FDTD code, so we need to account for that Y PML. But in 3D, we'd also need to account for Z. EY and HY, you only need the X and Z PMLs, and EZ and HZ, you only need the X and Y PMLs. And again, since we are doing HZ, we need to account for the Y PML. So that's it. That's all I have prepared for this video. You've now seen what PMLs look like in 1D, and in 3D, it's very much the same. So yeah, I hope, I guess my next video, or maybe in 2 videos from now, will be an FDTD in 2D with Python video. So hopefully you're excited for that. I'm going to be posting the code from this video on the GitHub, and you can find the link in the description of this video. Thank you guys so much for watching. This has been Computational Nanophotonics Video. I'm Josh. Have a great one.